So, if you look at the temperature distribution, temperature gradient in resistance spot welding, temperature gradient is extremely high. Okay. So, therefore, the heat affected zone, the width of the heat affected zone is very low, okay, very small. So, why? Because of the effective heat transfer in the process, right. If you look at this is the cross section, the FEM simulation which we carried out, and other point is it is very difficult to measure the temperature by experiments. Okay. If you attach a thermocouple, it is very difficult to get the temperature. Why? Because you are passing a current. If you attach the thermocouple, that will also influence your temperature measurements. Pyrometer, how do you measure? Because the weld is not exposed. Okay. So, the weld is contained. You will be measuring only the surface between the electrode and the sample. Okay. So, that is always it is cool, is not it? So, the best way is to simulate for a given condition, and the physics is well established. Okay, whatever I talked about I square r, that is it. So, once you know precisely the contact resistance, everything can be calculated. So, trick is to get the contact resistance. Okay. So, once you know the contact resistance, I square r t and then q by mCp, that is it. So, then we can solve for heat transfer, conduction and then convection, radiation, we can solve for it. Then we know exactly the temperature distribution in the weld nugget side. Okay. So, then we can get the exact temperature distribution from room temperature while applying whatever thermal cycle, so enhanced thermal cycle or the other thermal cycle. Yes, it is clear. So, this is a typical weld thermal cycle you get. So, again this is 1.2 mm, I am sorry because I like 1.2 mm. Okay. So, this is 1.2 mm thick plate. So, if you look at the temperature distribution, so the maximum we can go, so this is again the cross section. So, this is the cross section of the electrode, the entire cross section, okay, and this is the center. So, now if you look at the temperature distribution, so you form a fusion boundary, so where below which you have a the heat affected zone and above which you have a weld center line. Okay. So, the nugget we form generally it is an elliptical shape. Okay. So, but so you will have something like this, and can so the flashing happens. So, for example, this the fusion boundary extends to the surface of the plate. So, then you will have splashing, is not it? It is clear. So, if you look at so this is the temperature distribution, and you already reach to close to room temperature, somewhere about the 1 mm from the fusion boundary. Okay. So, already from say 1400 centigrade you reach to room temperature within 1 mm distance. So, the temperature gradient is extremely high, and due to that you minimize the heat affected zone significantly. But the problem is not due to heat affected zone in resistance spot welding. The problem is because of the weld center line segregation. So, suppose if you solidify this nugget, the solidification would happen in a columnar manner, right. So, you will have a grind core happening like this from the fusion boundary, they grow like this, and if you look at this growth, so obviously the liquid which solidifies at the end is at the middle at the weld center line, is not it. So, that is the region, it is the highest temperature you expect. So, that is the region it solidifies at the end. So, the alloying elements which are partitioning from the solidifying solid to liquid will all enrich the weld center line, right. So, that is the brittle region in this entire weld nugget because of the enrichment of alloying elements. So, now if you are after welding, if you apply a load, say for example tensile load, shear load, so you already have an interface which is not joined here. So, this is like a notch, is not it. So, it is like a notch, and you pull plates apart. In engineering application, for example, you apply a load, okay, and then you expect the stress concentration to happen at these regions, is not it. And then if you have a very brittle weld center line, the crack would go up and continue, and then the well will fail completely. So, now trick is to avoid such a failure. So, that is why we use the post well thermal cycles, okay. So that now we can homogenize or we change the microstructure in these regions, so that we arrest the crack propagation from the edge of the fusion boundary to the well center. It is clear? So this slide shows the temperature distribution. You always say the temperature gradient is very high, extremely high, because of the effective heat transfer from the well to the electrode. So you would expect maximum temperature gradient leading to minimization of heat affected zone. Okay. So if you are moving, say, even from 1 mm from the fusion boundary, the material will be in room temperature. It's clear? Good. So you can look at a thermal cycle. So for example, I showed you one at the center and one at the edge. Okay. You see the time. Okay, so it's hardly 400 milliseconds, isn't it? So material is heated up to a temperature at the center as high as say 800 degrees centigrade, 2000 Kelvin. Right, imagine material is heated up from say room temperature 2000 Kelvin in 100 milliseconds. So extremely fast heating as well as cooling rate. Okay, so within no time material is cooled from a melting point to room temperature. Okay, so the heating rate and cooling rate can be as high as 1000 to 2000 Kelvin per second. In this case even 4000 Kelvin per second. So this is the actual predicted thermal cycle for a weld I showed you in the previous graph. So the entire weld thermal cycle can be completed within half a second. Right. So the weld is formed, that is it. So this is what makes this process very attractive for the production, where you have to make 5000 welds in 2 minutes. Okay. So we will have 4 or 5 robots, okay, and then they would do all the jobs within 2 minutes. The entire chassis is welded, right. So because of such a fast heating and cooling we use. And even if you apply on a short pulsing subsequently, it does not take more than 100 seconds extra, right. So the entire process can be completed at an extremely rapid pace. Yes, it's clear? Good. So if you look at the schematic of the well nugget which is actually formed, so you always have a columnar growth from the fusion boundary. So this is again the base material and the copper electrodes. So if it is liquid, then you will have a columnar growth which is formed from the solidification from the fusion boundary, and in a steel or even aluminum alloys, so you always have a segregation at the liquid which is left unsolidified, right. So in this well nugget, the well center is the last solidifying region. So all the alloying elements which are segregating to the untransformed unsolidified liquid would enrich the regions at the well center line, and also at the solidification primary grind boundaries, right. It's clear. So unless you do some magic, so this weld is going to be very brittle. Okay. So as such, for a say low carbon steel or simple steel, you don't have any problem because segregation is not that significant. So the moment you increase the alloying elements, okay, so you will end up making a weld brittle because of the segregation of the well center line due to the solidification pattern. You always have a columnar growth growing from the fusion boundary towards the well center line, because that is how you extract the heat, isn't it. So you will have a very steep temperature gradient, and then the well solidifies from the fusion boundary towards the well center line. clear? Yes or no? So apart from that, you also apply a load, right? It's clear? So that will also influence the stresses that are developing during solidification, right? It's clear? So the both will influence the cracking in some alloys. So this is a typical microstructure of resistance spot weld. Okay, so whatever I explained. So this is the cross section. You see that notch? Can you see that? So this is the top and this is the bottom plate, and I have a beautiful weld nugget. Okay, so again this is 1.2 mm. So the weld nugget is typically about 4 mm weld nugget diameter. The cross section. So this is completely the molten, and then if you look at the actual microstructure, you have a columnar growth, isn't it? You see that it's not very clear, but you can see that the growth has happened, and here. And if you look at here, so that's what I talked about. So this is like a simple CTOD sample, isn't it? What is CTOD? Impact testing. What do you call? How do you make impact testing sample? Notch. How does it look like? Notch impact sample. Isn't it? Something like this. So you'll have stress concentration leading to a failure. And if you look at the structure, it's exactly like that. So you'll have a notch, right, and then a segregation at the center line, and this is a potentially very vulnerable structure, right? So because the stress concentration at the notch at the fusion boundary can be very huge, but you'll have to make sure that this weld is intact. Otherwise, when you make a car, then you hear something. So when weld is broken, you could hear. Good. Any questions so far? Good. We'll move on. So the electrodes, the type of electrodes what we use. So there are about 6, in fact 7 nowadays. So most commonly used electrodes are shown in this figure. So if you look at the cross section of the electrode, I will bring next class that electrode, you can also look at it. So the most commonly used electrodes are the type E, okay, and then type B. So based on the needs we can choose, okay, and we can also change the electrode diameter from top to bottom. That is also very useful. So for some reasons we can also change the diameter from top to bottom, that we will see in subsequent classes. But as of now, most commonly used electrode types are listed here. Okay, so if you look at the cross section, so this is the channel for water. Okay, so water goes in there to cool the electrode. Okay, so this is the phase. So you may have a type A, it's a pointer type, or a dome type. So in our lab, what we have is a dome type electrode. Okay, so if you look at so something like this. Okay, so you may also have a truncated type. This is also very commonly used electrode. Okay, so or flat, or even also have some concave radius. So it's also useful. Some eccentric electrodes. So this is all governed by the standard ISO standard 5182, okay, which actually governs the electrode selection, electrode material. So most commonly used the material for making electrode is copper or copper alloys. So obvious reason is it has to have a good electrical conductivity, also thermal conductivity, so that the heat can be extracted very effectively, right, from the fairing interface. The electrodes would not melt. Okay, so if your electrode is melting, then you have a problem. And electrodes would also withstand large number of weld thermal cycles. Okay, so if you use copper and you are welding a galvanized sheet, Okay, so what will happen? So most likely the zinc would diffuse to copper, then what will happen? Yeah. So you have an electrode on top and you have a material which is galvanized. If zinc diffuses to copper, would you form brass? Isn't it? So it's a big problem. So welding of automotive steels, especially when the steel is galvanized, so the electrode surface wears out, because the moment you form brass, you also change the resistivity locally, and you also increase the hardness. The layer becomes very brittle. So you will end up changing the nugget diameter. Even if you use the same current, same welding time, after 1000 welds, your weld nugget diameter will increase. So even it can lead to splashing if you are operating it close to Imax, right. So the electrode worn out is a big problem because of the use of copper and copper alloys for welding zinc coated steel. So there are various development has happened in the material. So for example, people started using even a rare earth addition. So adding yttrium oxide, okay, or zirconium oxide to copper to make it by a powder metallurgy route. So obviously these oxides enhance the electrical conductivity, okay. So they can improve the electrical conductivity, so that now we can avoid, we can increase or you can improve the mechanical properties of these electrodes, okay. So people thought about replacing the conventional copper with rare earth added the electrodes, copper electrodes, or even entirely replacing copper with the other super materials, for example cobalt chrome, okay. So you can also achieve a reasonably good thermal and electrical conductivity by these cobalt chrome alloys, and these alloys have a very good ice temperature properties. Good. So these are the common type of electrodes we use, okay. So most commonly we use type E and type A. Good. So as I said, the thumb rule for ideal weld nugget diameter is 4 times square root of thickness, and it is also governed by the automotive industry, okay. Sometimes it will be 4.2 times thickness, okay. So it does not matter. So the ideal diameter is 4 times thickness. So in order to achieve required diameter, and we will have to generate what is known as weld growth curve. That's what I explained in the introduction, okay. The weld growth curve is extremely significant to achieve to arrive at required weld nugget diameter, and this is also influenced by the mass, the m, okay. In turn mass is influenced by thickness as well as the Cp, specific heat capacity. So if you change the chemistry slightly, if you change the thickness slightly, weld growth curve changes, okay. So that makes this process extremely unstable for even a small change in processing conditions. So if a thickness is changed from 1.2 to 1.4 mm, you cannot use the same current and same welding time. You will have to invent the welding current, welding time required for welding for the change in thickness, okay. So the welding process parameter what you develop, it is extremely unique to a given thickness for a material, because m changes, isn't it. So obviously m change, even if you keep a Cp change, then I or T changes, okay. So to developing welding process parameters for resistance spot welding is a very laborious experiment. Suppose if you want to use a material, you are developing a steel for an application, so you will have to generate such a weld growth curves for varying thicknesses, and then give that to a customer, so that the customer can choose a welding parameter for a thickness what he is using in some area. You may use a different thickness in different parts, so then the same welding parameter cannot be used, right. So how do we generate such the welding parameters? So we get the weld nugget diameter measured as a function of current by fixing the time constant, or as a function of weld time by fixing the current constant. Okay. Generally the strength is proportional to the well nugget diameter. Diameter is higher, that means that strength is higher until the expulsion. So, what is expulsion? So, this is the maximum current at which the liquid is expelled, right. So, that is expulsion, so the I max. So, in this case this is I max, is not it? Now, so we can generate such growth curves where you change the current for a given time and measure the well nugget diameter. Okay. So, once it becomes I max, obviously, and you start off expelling the liquid which is there in between the welding electrodes, and then the strength decreases because you will have a cavity, the liquid is going out. Okay. So, that is the I max what you have, and you can identify. So, now you suppose if you want to get a 4 square root of thickness, you can identify, say suppose this current would give me the diameter of a 4 square root of thickness. Okay. And this is to identify the current required. So, once you identify the current, so you can also vary the time, is not it? So, time for a given current would also change the well nugget diameter, because I square RT Q is a function of current and then time, because contact resistance is fixed as long as load is fixed, is not it? So, you can also get a well nugget time generated for a given current and identify the optimum well time required to generate a nugget diameter of your interest. It's clear? So, you will have to identify the I max. So, the I max is the maximum current above which expulsion or splashing occurs. So, expulsion and splashing, they mean the same. So, the I max is the maximum current above which expulsion or splashing happens. Okay, it's clear? This graph is clear, right? Yes or no? Okay, we will move on. So, applications. So, I just put one example. So, this is I think Ford Fiesta. Okay. So, I think it is 2010 model, I remember correctly. So, if you look at this is a body in white. What is body in white? It is not human body, it is a car body. Okay, so it is called body in white. And then if you look at the parts, so all these the pillars, you see the black dots, these are all wells, resistance pot wells. Okay, so these flanges, the pillars and all the parts are all joined by resistance pot weld. Okay, so you see the dots here. I don't know, it is difficult to see. Okay. So, in a typical car, automotive car, you have about 2000 to 5000 spot welds. Okay. So, number of welds you make per day in India, it will run around a few crores. Okay. So, the statistic I took it from TWI, the Welding Institute of London. So, in Europe alone, they make about 15 crore welds every day. The similar amount you also see in India as well. Okay. So, the number of welds, resistance pot welds is made in a day, it is huge, enormous. Okay. So, we will have to make sure that by obtaining a good welding procedure, so these welds can withstand the life cycle of an automotive vehicle, right. So, the typical life of an automotive is 300,000 kilometers, 3 lakh kilometers. Okay. So, the well should be intact. So, if well breaks when the monkey jumps, then you have a problem. Okay. So, then as a welding engineer or as a welding scientist, and we have a problem in hand, we will have to solve that. So, in by nature, the resistance pot weld is one of the worst geometry you can generate. Okay. So, because of the well segregation, the notch effect. So, this is the worst thing you can have, but we will have to live with that. So, we will have to identify the well thermal cycle which can give us the improved mechanical properties. Okay. It is always the welder's job. Okay. So, steel the metallurgists who are developing steel, they always curse us, the welders, because they would generate such a beautiful microstructure, with all the properties. They want strength, ductility, toughness. Ultimately, you have to weld, otherwise you can't make a car. So they always tell us, okay, you guys always destroy such a beautiful microstructure. Okay, so but that is how we will do it. But still, the demand is the weld should never fail. Okay, so weld should never fail. The failure should always happen, except weld. In anywhere else except weld. So even though we have such a challenging geometry, we can make a weld which can withstand the demanding load cycles. Okay, so that is a challenge. So we can work on. So we will see in how we can improve, how we can achieve the required mechanical properties of the welds, resistance spot welds, without going much in detail of the microstructure. Okay, it's good. So this is common thermal cycles. We use it for the alloys, like for example mild steel, the zinc coated, or deep zinc coated, and the electro galvanized material. If you look at comparing the bare sheet, you always need to have a higher current, isn't it, for zinc coated steel. So in this case, the mild steel is operated between these regions. Okay. So and then this is for electro zinc coated. So you have to soften the galvanized layer. So you need to pass a ramping current, so that you soften the zinc coating layer, and you also by doing so increase the weld time in cycles. You see that weld time in cycles. So you never give weld time in resistance spot weld in seconds. You always mention in cycles. Okay, so for example, if 10 cycles means, so it will be 200 milliseconds. Okay, it's clear. So we generate such a curve. Okay, so the one weld growth curve what I am showing here, so as a function of current and then time. So we can also generate the window in which you can operate for a given composition and the thickness. And this table shows the compatibility, the weldability, and this I took it from a handbook, and this was very important. Suppose in future if you want to know that can I weld aluminum to steel, which is very difficult, don't try. Okay, can I do a steel, okay, you can do. Okay, so you can choose by looking at this table. Okay, so whether I can weld say for example aluminum to aluminum, it's B. Okay, so you need to get an enhanced weld thermal cycle so that you can reasonably weld. Okay, aluminum to stainless steel, never try. Okay, impossible. I will challenge, I will bet you. I can even recommend for Nobel Prize. If you generate a weld of aluminum stainless steel without any crack. Okay, so the most preferred the A's. So A's will be steel to stainless steel, reasonably okay, and steel to steel, it's very nice, happy. Okay, and if you go beyond lead and zinc and things like that, it's very difficult for you to get a good weld nugget diameter. Okay, so you can refer this table. So I just put it from the handbook, so that now you can identify the weldability for varying interfaces. Okay, so other important considerations apart from the current and time, so what we will have to consider is the geometry. Okay, so geometry of the weld, one of the important factors you need to consider here is the distance between the weld. Okay, so for example, if you have an overlapping distance of L, where exactly you will place the weld. So you will always place the weld by a distance, half a distance, okay, between the L. So this is the overlapping distance. So L by 2 you place the weld, and then the distance between the weld is extremely important. Okay, because that is going to determine the path of the electric current. Okay, so the S and L by 2, generally we have a weld placed in overlap configuration, or half a distance between the overlap, and the S is the distance between two welds. And this is very critical, yes. So why it is very critical? Okay, we'll get back to that in next class. But as of now, you can assume that the S is also very critical. If you keep it very close, then you may also have a current pass through the previously welded nugget. Okay. Suppose if you are welding it in this case, so if you are keeping it very close, so instead of the current passing through this location, it finds another easy way, because this is a solid junction now, there is no contact resistance, isn't it? You already made a weld nugget. So current would follow the easiest path, it will start flowing, it will start reheating the already formed weld nugget. Okay, it's clear. So instead of that, instead of making weld here, you will end up heating the weld nugget here, previously made weld nugget. So that's why the S is very critical, the minimum distance between two welds. Okay, so there are some data you can find it out. Okay, so these are already established for the parameters for low carbon steel as a function of thickness. So what is the minimum S you need, what is the minimum overlap distance you need to have. Okay, and these are all calculated based on the fact that the electrical resistance or the contact resistance will be maintained at the fairing interface. And yeah, no need to concentrate on this I just show you to see that these are important. Okay. And then another geometry considerations when you are doing spot welds, it is never advisable to do such a weld, because obviously the load distribution will be extremely bad in this case if you are doing welding. It is always advisable to and zigzag welds, and this will be much stronger geometrically than a structure like this here, isn't it? So this zigzag spot weld would result in balanced force and minimal distortion, isn't it? It's obvious. So that's why when you are welding it, it's not advisable to weld this configuration. So we always good to weld this configuration. Yes. So this gives the balanced force as well as minimum distortion. So some of the geometrical considerations, because here load distribution is very important, right? So you can look at say for example, if you are having a very short L angle, it's not recommended. Okay, you can do it, but ideally you should do it in an L flange. Okay, so similarly instead of having a well like this, and you can have a longer distance, and you can also have a lot of geometrical considerations. Okay, the structural analysis is extremely important in spot weld, and all the automotive components, they optimize the structural load distribution, and then they identify where exactly they are to place the weld nugget. Okay, so you cannot just like that you choose a point and weld, because the load distribution is a function of geometry of your component. So the structural analysis, they do it for a component, and they identify the location where it is ideal for the spot weld to be there. Otherwise you will end up not balancing this force, and you induce a lot of stress partition to the weld nugget, and weld is prone for failure, right? It's clear. So we will also look at the testing, so how we can quantify the weld nuggets, maybe in next class. Okay, good. Any questions so far? Yes or no? So we looked at in this class weld thermal cycles, simple weld thermal cycles, the enhanced weld thermal cycle, and then mass effect, the effect of thicknesses, and then we looked at the weld growth curves, Imax, and then we looked at the temperature distribution, temperature gradient, right? So cooling rates, right? The width of the weld nugget, and then the heat affected zone, and we also looked at some geometrical considerations, the L and S. Okay, we look at in next class how we can test, or what are the testing methods we use to quantify the mechanical properties of these spot welds. Right, good.